Very good morning. We are continuing with factor analysis. Today we discuss parameter estimation. We discuss estimation of factor loadings and estimation of specific variances. We discuss principal component method as a method of parameter estimation for factor model. Let's go to the next.
We will continue factor analysis. Today our discussion will be on two issues. First one is model estimation, then followed by model adequacy testing. Both related to exploratory factor analysis. Both related to these two. Now what we have seen in last class, that the exploratory factor model is this: lambda f plus delta, and the variance structure is like this: sigma equal to lambda transpose plus psi. Okay, this one is P cross P matrix, this is P cross M, this one is M cross P, and this one is P cross P diagonal matrix. Okay. By estimation, what we mean to say, we want to estimate lambda. The estimate of lambda is lambda cap. We want to estimate psi, that's psi cap. So we can say, now what is known to us? We know that is capital sigma cap. This one we can assume as S. This is also P cross P matrix. So then how do I go about for estimating these two? One is P plus M, P cross M vector, another one is P plus P cross P vector, but where this error term or specific variance term is diagonal. Okay. So essentially, suppose you have collected a data N cross P matrix, this on P variables, Px variables basically related to x, and you have computed S also P cross P. Now if we think that the sample size is large and sampling strategy is appropriate, then we can say that the sigma estimate, which is basically sigma 1 sigma 1 2, like sigma 1 p, sigma 1 2, sigma 2 2, sigma 2 p, like this, sigma 1 p, sigma 2 p, sigma p p. These estimates, which is basically S, where S is S11, S12, S1p, S12, S22, S2p, like this, S1p, S2p, SPP. Correct? So these are the estimates which in general, if I say sigma jk, that estimate is sjk for j equal to 1 to p, k equal to 1 to p. Now we can assume that under good estimation, that what will happen ultimately, if our sampling size is appropriate, adequate, and we are able to capture properly the behavior, covariance structure, show that sigma jk equal to sjk. That means what I mean to say here, I mean to say that each of the element in capital sigma and this is, this will be very close, very close. So we have P cross P matrix here, and number of estimating parameters will be here, half into P into P plus 1 into P. This many parameters, because if you see the structure here, you see this portion is mirror image of this. So ultimately if it is not this P cross P, it is other than this value. Okay. That means essentially what we are estimating here, or what we are assuming here, we are assuming that we want to estimate something that is sigma, which is lambda cap lambda transpose plus psi transpose. That is what we want to do. Basically, using these estimates, we want to find out these values, estimate of these values. So other way what we will do, we also don't know this one, we know S only. So we initialize values for this lambda cap and psi cap, and then we find out this value. Then we compare this value with S, individual elements of the vector, and we find out a situation where the difference between element of these two matrices will be as small as possible within certain threshold limit. But what is in factor analysis, what you will find out that the each variable variance is a key issue. So when we talk about stress of this is nothing but the sum total of j equal to 1 to p, sum total of sigma jj, that means the variance of each of the sum total of variance of each of the variables. That means similarly if I say stress of S, that is also j equal to 1 to p S jj. So instead of then we require, what we require? We require a function to be minimized. Now if we go for the least square estimates, squares estimation, then what you will find out that we require to minimize the error. What is error here? The error is the difference between the two. Okay, so our sample covariance matrix is this, population covariance matrix is this, and we want the minimization function which basically minimize the sum square errors, that means sum square of the elements of this matrix. Here we will consider, as we are interested in the variance component, we are considering here that sum square error like this, and for, so this is in the matrix domain, so this will be like this will be this, and then we take, basically we minimize a function related with g, which is trace of this. Okay. So essentially this leads to that norm, second norm, this we can say instead of S, if we write lambda transpose plus epsilon plus psi. So this is what is sigma. Okay. So we want to minimize this function, So what are the thing you must know? See, if you want to minimize, then you take the derivative that by maximum derivative of this, and then with respect to the parameters put it into 0, and then you get this value. This is the standard way, general way we used to do when we have the very simple functions. Here there are problem is that you will find out that your lambda, capital lambda as well as psi, these are the unknown parameters. Okay, if I take with respect to lambda, and what is required here, we require to know particularly we have to initialize the values. So as a result, what is required, we require an initial estimate of psi. Initial estimate of psi, this is one. The second requirement is how many factors we are extracting, m factors. What is this value? Value of m. That value also you require to know. Essentially, if we look into the factor model, number of parameters to be estimated as well as that what is the degrees of freedom available, then what we will find out, we find out that the degree of freedom is number of parameters for that capital sigma. This is unconstrained, and minus number of parameters for sigma constraint. Okay. In the unconstrained case, the total number of parameter will be half p into p plus 1, and when you make a constant case, that is pm plus p minus half m into m minus 1, and this will lead to half of p minus m square p plus m. Okay. So this is what is the degrees of freedom available. Now, if your degrees of freedom DOF is 0, you will get a unique solution. If DOF greater than 0, you have several solutions. So, and if DOF less than 0, it is not determined. So, we can say the factor model is indeterminate. Okay. The general situation is this. This is the general situation. So, what we want, as we will be getting large number of solutions, because there is no unique solution in this case and it is overestimation situation. So, you require to put certain constants. Okay. That constant will be lambda, that psi inverse lambda, this transpose this will become 0. So, this will become, if this becomes 0, this will become diagonal. This become diagonal. That is the constant. This one is m cross p, this is p cross p, this one is p cross m. So, resultant will be m cross m. So, ultimately the diagonal elements, m elements will be there, and of diagonal elements that will become 0, and as a result you will find out that this is the number of parameter you are relaxing, you are basically fixing to 0, and ultimately you are getting this. Okay, that is what is we are saying about. So you have to fix that M in such a manner that your degrees of freedom should not be this, as well as we don't want also this, we want this situation. Now with this what I can say, with this background, I will now explain what are the methods available for estimations. First one is principal component method. Second one is principal factor method. And third one is your maximum likelihood method. Okay. First we describe principal component method. It is similar, it is basically what you have done in PCA. In PCA, you have considered the population covariance matrix, and we say that this one is can be decomposed. This can be decomposed into its eigenvalue and eigenvector pairs. Eigenvalue and eigenvector pairs. Okay. Actually, if I say that Qj is the eigenvalue and Ej is the eigenvector, in then what you can write? You can write that sigma is Qj, Ej, suppose Ej we are writing like this will be P cross 1. So Ej transpose, then summation of j equal to 1 to P. This is known as spectral decomposition. Okay. In PCA, when we described this, we instead of Qj, I have written this as lambda j, but in this case we are using lambda, that capital lambda, which is the component lambda 1, these are the factor loadings. So I am using Qj for eigenvalue. If this is the case, then can we not proceed like this, that this is my Qj, Q1 E1, E1 transpose plus Q2 E2, E2 transpose, like this, QP EP, EP transpose. You can write like this one in this manner. So similarly, this can be written Q1 root E1, Q2 root E2, Qm root Em, then Qp root Ep, multiplied by root Q1 E1 transpose, root Q2 E2 transpose, like root Qm Em transpose, root Qp Ep transpose. Okay. So if we denote this first portion as lambda, then this will definitely lambda transpose. Okay. So that means essentially we are writing that sigma is lambda transpose, and it is possible. You can verify this, it is very much possible. And in this case what is happening here, so there are p, so number of components extracted is p, and your this matrix is also p cross p matrix. So maximum possible component is extracted, and here definitely we are assuming that the rank of this matrix is definitely p, that is full rank, okay, in this sense. But in factor analysis, what is the purpose? Purpose that there are many variables which are correlated. So in that case we want much less number of factors, that is m, where m is less than p. So in that case, if I say that this is the domain of our m and similarly this much is for another m, then the remaining portion we can attribute to the error terms or specific variance, because if we do not extract p factors, which we also do not want, we want a subset of p that may be very small. If m equal to 1, that is the best, if m equal to 2, 3 or like this, but it must be the subset of this. So we are now making little manipulation here. What we are saying that I want to write that sigma equal to this transpose plus psi, where this delta 1 is nothing but we are considering q1 e1 root q2 u2, so ultimately root qm em, that we are considering. So that means remaining portion means root over q m plus 1 e m plus 1 to your qp and ep. This portion we will this portion multiplied by its transpose we will relate to this psi. Okay. If this is the case, then I can say that my first factor, if it is f1, okay, this factor is loading is root over q1 and u1, where u1 is the eigen vectors, which is u11, u12. So how many variables are there? P variables, p cross 1. So for factor 2, it will be root q2 e2. I am talking about the loading part. So similarly, your factor m, this is qm em. Once you have this values, but how do you get these values? These values will be got, you will use S matrix, that is the sample covariance matrix, which then will write this lambda cap transpose plus psi cap. Okay. So in this case your things will be like this, all will be cap, E1 cap, E2 cap, EM cap. Fine. So, using S, you will estimate this lambda, then, and that is through spectral decomposition of this S matrix. You will do the spectral decomposition S matrix, and then how do we get the psi? Psi you will be getting equal to S minus lambda cap transpose. Then what are the steps? Steps are find, suppose first step is find S, second step find out eigenvalues and eigenvectors of S. Okay. Then third one is you select M, and then fourth one is once you select M, then find out the loading, so obtain lambda, that is lambda cap. Then fifth one is obtain psi cap. So, how do you select M? It is a tricky one, but there are certain suggestions. So, if you, because you see this equation, you are interested to find out this value. So, this value is nothing but lambda cap transpose is nothing but S minus psi. What is this rank of this? Rank of, what I mean to say, find out the rank of this matrix. But you do not know psi. Here the way we are giving, you are basically finding out to this psi. So, if you go by this method initially, you first find out this one. There are methods to first select the number of factors that we will discuss. Okay, but if you initialize sigma 0, sigma cap as sigma 0 cap, then you find out this one, find out this rank, or if we also you can find out that what is this rank of this matrix, and then you can start with, but this principal component analysis, once you get like this, then using the eigenvalues, you can find out that how many factors you will keep. That you have seen in PCA, there are different methods of keeping the identifying the number of principal component to be kept. For example, that cumulative percentage, for example, your average eigenvalues, for example, the broken stick method, for example, your scree plot, for example, we have also gone for certain hypothesis testing there also. Okay. So, those issues I will under model adequacy test I will explain a little bit more, but at present we will see that using AS and principal component analysis or principal component method, how the factors can be retained. Okay, thank you very much.